And how do you even define that? Oh, thank you. Now I have, were you hearing me before? Yeah, okay. Maybe you can get really, really close, but how do you define that? Now this question of, what's the best you can achieve, that also requires you to prove lower bounds, which forces you to do a little bit of complexity theory, even if you really don't want to. But I don't have to do it in this class. I can just mention to you some of the results. And I will do that in a little while. But for now, we're going to talk about getting closer approximations. And in particular, I'm going to show you that for a few problems, so we have this general question of what is the best achievable. Approximation. And I will mention to you later on that for certain problems, there is some constant greater than 1 where you can achieve a C approximation, and the complexity theorists have actually proven that you can't do better than a C approximation unless P equals NP. Okay, so there are some problems where there are specific limits on how well you can approximate them. But we're going to go in another direction. We are going to look at a class of problems that can be approximated arbitrarily closely. And the way we formalize that is by talking about approximation schemes. So an approximation scheme is, for a given problem, a family of polynomial time algorithms, A sub epsilon, or sorry, let me just say it this way, a family of algorithms A sub epsilon, such that each A sub epsilon is a polynomial time algorithm, and A sub epsilon achieves a 1 plus epsilon approximation. Or put another way, A sub epsilon is a 1 plus epsilon approximation algorithm. That's more correct. Okay? So if you have an approximation scheme for a problem, then however close you want to approximate that problem, you can. There's an algorithm for doing so. Okay? Now, does this mean that you can get an exact solution? No, because here epsilon is always greater than 0. So there's no one approximation algorithm. There's just approximation algorithms for all the constants bigger than 1. Now, if you think about it, when you define this, this class, you can talk about the runtime of the algorithm as a function of epsilon. And that might not be polynomial. So all that is required is that each specific epsilon, you have a polynomial time algorithm. But it may be that as epsilon gets really small, the runtime of the individual algorithms turns into a worse and worse polynomial. Okay? And we're going to see that. So for example, if you have a family of algorithms, or one sort of meta-algorithm with a running time of n to the 1 over epsilon squared, okay, then for every specific epsilon, this is a polynomial time algorithm. Right? So whatever constant you want to achieve, you can in polynomial time. But in practice, it would be disastrous to try to use this for a small value of epsilon. So you might try and do better and define what's known as a fully polynomial approximation scheme. Which is one where the runtime is polynomial in n and also in 1 over epsilon. So, for example, n over epsilon squared. Okay. And, being polynomial, you kind of want to be polynomial in 1 over epsilon for the same reason that you want to be polynomial in n, right? We've sort of evolved this sense that polynomial time algorithms are, often ones that will run reasonably in practice, right? And so it's a good thing to aim for. Again, the polynomial can be so large as to make it unreasonable, but it sort of at least points us in the proper direction for algorithms that we might actually use. Okay. So today, I am going to show you a fully polynomial approximation scheme for knapsack, and then if there's time, I'll also show you a not fully approximation scheme for the load balancing problem. Okay. So let's look at a fully polynomial approximation scheme for knapsack. This is one of the many NP-hard problems that was defined in the first lecture on approximation algorithms, right? It's can also be sort of thought of as the shoplifting problem, where you have a collection of items where each item has a profit, PI, associated with the items. But each item also has a size, SI, and we'll use n for the number of items. Right, so profit PI and size is SI. And a certain knapsack size. Right, S. And your goal is to figure out the maximum profit that fits inside of S, right? How much can you sneak into your pocket in order to get out of the store without being caught? Okay. Or I guess another, more practical use for you is, if each MIT course involves a certain workload and also brings a certain amount of increase in future salary, right? How do you maximize your salary subject to actually surviving the 4 years at MIT, right? That would be another formulation of the problem. Okay. I'm going to show you a polynomial time algorithm for this, which uses what is basically the canonical technique for developing fully polynomial approximation schemes. And what we're going to do is we're going to start by considering the case of bounded integer profits. Right? So restricting to integers to start with is a good trick. We did it with scaling. Right? It's going to help us here too. We're not assuming they're bounded by a constant. It's going to be okay if they're bigger, but it is going to be important that they're integers, and the size is going to show up in our runtime. Okay? And once we have bounded integer profits, it's very natural to take a dynamic programming approach. What I'm going to do is I'm going to define a dynamic programming table where B of JP is the smallest size set of items from 1 through j that achieves a profit of at least p. Okay. Or a null if you cannot achieve that, if you cannot achieve profit p. Okay? So this is the natural sort of dynamic programming way to define this problem. Obviously, if it is possible to achieve a profit of p, there is some smallest size way to achieve that profit of p. And once you focus on the smallest size, you have the subproblem optimality that allows you to do dynamic programming. Right? What does subproblem optimality mean? It means that if you have an optimum solution to a bigger problem, it contains within it optimum solutions to the smaller problems. Okay? And in particular, let me ask you how I can express the optimum solution for the items 1 through j plus 1 at a target profit p. How can I assemble that by considering smaller problems? Yes?
Either we include the j plus 1 item or we don't.
Exactly. We do case analysis, right? Either whatever the optimum solution is, it either has the j plus first item or it does not, right? So that gives us two possible ways to get the optimum through j plus 1. So if the optimum solution does not include the j plus first item, then what defines the optimum solution for items 1 through j plus 1? Yes? Exactly. So one thing we can do is ignore item j plus 1, and then we just take the same solution involving items 1 through j. What's the other possibility? The other possibility is that we do include item j plus 1. And if we know that we are including item j plus 1, how do we complete the optimum solution? What do we add what do we add that item j to? What do we add that j plus first item? What can we say about the rest of the solution? Yeah.
You can subtract bj plus 1 from p, and that's for bj comma p minus pj plus 1.
Exactly. So the point is that if we're trying to achieve profit p and we know we're including item j plus 1, that means that we are getting profit pj plus 1 from it, which means that the rest of the solution has to give us a profit of p minus pj plus 1, right? How much space do I want to leave, right? Whoops. The rest of the solution has to give us profit p minus pj plus 1 using the items, whoops, my order right, items 1 through j and profit of p minus pj plus 1. Okay, so we get this solution, but what do we have to add to it if we're looking at the solution to this problem? Well, we have to add an item j plus 1, right? And so that costs us an additional size of j plus 1. Okay? So this is all we need for our dynamic program. Basically, each entry in the dynamic program depends on two entries from the previous row, right? The j plus 1 row only depends on row j, right? And it depends on two specific entries in that row relative to the value p. Is that clear to everybody? Okay. So to make sure, right, how big does this table have to get? Like, up to what size do we go? Well, where's the final answer? Yeah? Right, it's at size, well, let's be a little careful. So it's at row n, because we're considering all n items, right? But the second entry is not a size, it's a profit, right? We don't put an S into the second entry, right? So what do we do in that nth row? Yeah?
Search for the biggest profit?
In the entire row, well, so if you think about it, as we move across the row, we're getting bigger and bigger profits. So what does it mean to search for the biggest profit? What constraint do you have to, yeah?
Yes, we could throw some p such that b and p is defined. Because we didn't mention the boundary conditions.
Well, so we do need to think about the boundary conditions. So the first boundary condition is what we do at j equals 0, right? Where the answer is just, it's empty everywhere, right? There is no solution. Sorry, except at p equals 0, right? You can achieve 0 profit with no items. So you start with that.
Zero p to be infinite.
Yes.
Then we are looking for a p such that b and p is finite.
Right, so that's the constraint, right? So in the final row, we find out the minimum size way. Well, finite is not enough, actually, right? The final row will show us in each position, right, at each p, it will show us the minimum size way to achieve profit p. So what do we need to look for in that row? Yeah?
We're looking for the maximum p such that b and p is less than or equal to s.
Exactly. If you think about it, as you move along this row, we're asking for more and more profit, so the size demand is going to go up and up, right? At a certain point, it's going to cross our threshold S, which means it's gotten too big for us to collect, okay? Let's see, how do I say this? It's actually an argmax. So we want to take the argmax over p of b of np. Sorry, my notation is going to be silly here, but such that no, let me be more precise about this. At the maximum p, such that b of np is at most s. Right? You scan along that row until you find one that is, you find the biggest one that's less, that takes size less than s. Okay? But this actually raises another question, which is to figure out how far out we need to build the rows. Like, maybe we have to look infinitely far out in order to figure out, in order to find the p, the maximum p. Right? So where are we going to run out? Where can we stop moving? Yeah?
You could look at which item is like the most efficient item, like which one gives you the maximizes profit divided by size, and then do that number times the s.
That actually raises a very important distinction, qualification here, which I took for granted but should make explicit. In the standard knapsack problem, you can only use each item once. So you're only looking for a set, not a multi-set. Okay? If you want to allow items to be reused, you can just make extra copies of those items in your collection, so it doesn't actually this restriction is more general. Okay. But if our plan is to build this table, we still need to know when to stop, right? So, at what profit p can we stop? Yeah. Sure. Right? We can stop at p equals the sum of the profits because we know that you can't do better than the sum of the profits. Okay. All right. So that gives us the size of our table. Now notice that in fact, if we know p, we can stop there. Or if we know opt. Right? Or one past that optimum. Right? So if we know what p we can achieve, we can just move out to that p in order to know what space is required for that p. Right? Now I'll also mention something else here. Here we've defined it only in terms of finding values of the optimum. But does everybody see that we can also use this to actually construct the optimum set? This is, again, sort of a standard thing from dynamic programming, right? You generally express your dynamic program just in terms of the value of the objective, but implicit in that is the actual solution to the problem that provides you with that value. Because you can look back at which choice did you make to fill in each entry of the dynamic programming table, and that tells you whether to, right, if you start at the optimum value, you can trace back along those choices in order to figure out which items are included. Yes? Okay, so I won't do that. I won't fill that out in detail. And so this means that what's the runtime of this algorithm? Well, it's just the time to build this table, and we've just figured out how big the table is, right? Namely, there are n rows, and the number of columns that we need to walk out is just the optimum value of the solution. Okay? But as was observed, this is at most n times the sum of the pi's. Right? Okay. So now we have a polynomial time algorithm for knapsack, right? That's a polynomial. Does this prove p equals np? We do prove some pretty amazing breakthroughs in this class, but did we prove that one? Yeah? Right. So this goes back to what we saw in Maxflow. This is a pseudo-polynomial algorithm. The runtime depends, or is polynomial in the values of the numbers, not in the bit sizes, right? Because again, you only need a logarithmic number of bits to represent a number, and therefore, this is actually exponential in the number of bits that you put into the numbers. Now, if your numbers are polynomial valued numbers, then the whole algorithm is polynomial time. So this does not require that your numbers be 1 or 2 or 3, right? It's not small constants. Your numbers can be large polynomials, and the runtime is still a polynomial. The problem is that with a size n problem, you can use n bits to represent your numbers, and that means you can represent exponentially large numbers. And if you do that, then your runtime is going to be exponential relative to the number of items. Make sense? Okay. So, yeah, it's a pseudo-polynomial algorithm, but it is not a weakly polynomial algorithm. Okay. But now we have the sort of obvious, more general question: what if we don't have integers? What do we do if somebody gives us rationals? We don't need to worry about reals because they can't be represented in the computer, but somebody could certainly give us fractional sizes for our items. What should we do? Yes?
Clear denominators and just use.
Okay, so one thing we could consider is clearing denominators, right? Turn everything into integers by multiplying everything by the lowest common denominator. This is problematic. How come? Yes?
The numbers get really big.
Yeah. If I have n items and they all have different, prime number denominators, then the product of all of those denominators that I need to use in order to clear out the denominators is going to be an exponentially large number. Right? So even if the numbers started as polynomial size numbers, I'm going to get exponential size numbers, and when I try to run this algorithm, I'm doomed. Right? I mean, even before we go to rationals, there's the question of what can we achieve if the numbers really are super polynomial integers. Right? This algorithm is not polynomial if the numbers are super polynomial integers, so what should we do? So actually, that might be a more intuitive case to think about than the rationals. Right? Suppose that you just have these gigantic integers, so you can't afford to take time polynomial in their values. What might you do to fix that problem? How might you, say, make those integers smaller? Yeah?
You could maybe round them to like smaller precision.
Exactly. Right? If the integers are too big, let's just round them down. Okay? Intuitively, right, if we scale all of the integers by the same number, by the same amount, right, we multiply all of them by 1/1000th, we're not really changing the knapsack problem significantly, right? The problem is that if we literally multiply all of them by 1/1000th, they might not be integers anymore, and so we can't use this algorithm. So we want to round them down, but we also want integers. Okay? And so to do that, we are going to combine, right? So to generalize this, we are simply going to scale and round. And for starters, to make this easy, I'm going to assume that I know the optimum target profit P. Okay. So I know P. I want to make the values small so that my pseudo-polynomial algorithm is fast. So what I'm going to do is I'm going to scale all the profits from pi. I'm going to scale them by an n over epsilon p factor, which is going to make them small, right? By dividing by p, I get rid of the possibly huge size of the profit. The n over epsilon is going to make my epsilon approximation work out. We'll see that in a minute. But now, in order to make it an integer, I'll just round down to the nearest integer. Okay. So just the scaling does nothing to the problem, nothing of interest to the problem, right? The optimum is still the optimum. I've just scaled its value, right? But rounding down, that perturbs the values of the individual items. So that's going to matter. Okay? But how does it change things? Right? What can I say about the new optimum? I can't say what it is exactly, but I can bound it. So what sort of bounds can I put? So for example, what sort of upper bound can I put on this new optimum? Yeah?
The up before you rounded it?
Yes, exactly. In the best case, my scaling is going to produce integers, and rounding isn't going to change anything. right? So if every solution just scales and doesn't get rounded, then in particular, the optimum solution is going to scale by this n over epsilon factor, n over epsilon p factor, and so the optimum solution is going to turn into n over epsilon, right? Everybody agrees with that? Okay, what about a lower bound? How bad could the new optimum be? What's the worst thing that could happen when I do my rounding? Yes? Well, if they become zeros when I round, what were they before I rounded? Yeah.
At most, like slightly less than 1. Or in the worst case, all of the things you're flooring get floored by the maximum value.
Exactly. The point is that since I'm just rounding to the nearest integer, at worst, I'm losing 1 unit of profit from each item, right? After rounding, right? So with scaling, my optimum solution starts out at n over epsilon, and it is made up of at most n items, each of which lose at most 1, or slightly less than 1, which means that altogether, I'm going to lose at most n, right? And I can rewrite this as n over epsilon times 1 minus epsilon. And so this is the reason for this n over epsilon term that I've put into the scaling, is that it means that my new optimum is perturbed by at most a 1 minus epsilon factor. Okay? Okay, now that we've got that new perturbed optimum, we can use our dynamic program to find the optimum of the rounded problem. Right? How long is that going to take us? How big do we have to make the dynamic program? Well, the no, oh yes, yeah.
So squared over epsilon.
How about?
Because previously it's like n times the total profit of
Exactly. The runtime that we just analyzed is n times the optimum value that we're looking for, right? Which in this case is at most n over epsilon, right? And so that's the point. We go out until column n over epsilon, and that guarantees that we'll find whatever the scaled optimum is, right? So n squared over epsilon runtime. Okay. So we will find a value equal to the new optimum, right? The scaled optimum. What do we do now? We have a solution to the new problem, but we want a solution to the old problem. What should we do? Yes.
You can scale each element and the new solution back up to 1.
Exactly. We're going to use the same solution. Right. So let me write this as what notation do I want to use here? Sorry, sometimes I tend to run out of letters. Yeah, let's call this Q. So we find this new q. We just use it as a solution to the old problem. And so what's going to be its value in the old measure before scaling? What happens when we unscale? Yeah.
Multiply by epsilon p over n.
Exactly. We get back what we lost. Now, in fact, we start by unrounding, but we can't actually say what we gain from the unrounding, right? Our solution may have been integer, and we may get nothing back, right? But we certainly get to unscale it, right? Which means that its value is going to be epsilon p over n times q. Right? Now, how can we relate that to what we're actually trying to find, or to the value actually we want, right? The value p. In other words, how can we get q out of that equation, because we don't know what q is exactly? Yeah?
Q is n over epsilon.
Exactly. Right? We showed a lower bound on the scaled optimum. And so, of course, the epsilon over n is canceled, and we're left with p times 1 minus epsilon. In other words, we've got a solution which is within 1 minus epsilon of the optimum. And it doesn't matter how big p was. And so what we have here is one of these fully polynomial approximation schemes, right? In order to achieve an approximation that's accurate to within epsilon, we have a slowdown by a 1 over epsilon factor, which is polynomial in 1 over epsilon. Now, there is a detail that we need to fill in, right? I assumed p was known. What do we do if p is unknown? Yeah?
Just binary search.
Binary search. Right. So, and inside of that binary search is the answer, which is to guess, right? Let's just try and guess what p is and see what happens, right? So imagine that we guess some p prime. Okay, so that's why I didn't want to use p prime before. What's going to happen? If we guess p prime, then our scaling is going to go to n over epsilon p prime times pi, right? Which means that the optimum, the scaled optimum, just applying the same arguments we did for known p, is going to be at most np over epsilon p prime, and at least np over epsilon p prime minus n. Right, we're still going to lose n from the rounding, which can be rewritten as n over epsilon times p over p prime minus epsilon, right? Yeah, that's right. And we can use these two bounds the same way as we used our accurate knowledge of p, right? We can say that we only have to look this far, it puts a limit on how far out we have to build the dynamic program. Right? Of course, in order to know how far you look, you have to know what P is, so we may have a problem there, but I'll come back to that. Right? But we also know that we will find a solution of at least this value. Right? And so if we unscale this solution, right, then the value that we get back is going to be at least, we're going to undo the scaling factor, so now we have epsilon p prime over n times n over epsilon times p over p prime minus epsilon. Right? Again, the n over epsilons cancel, and what we get back is p minus epsilon p prime. Okay. So we still have both p and p prime showing up, but one thing which will make all of this very nice is if, for example, we use a lower bound. We ensure that p prime is less than p, right? If we choose a lower bound, then this is going to be at least 1 minus epsilon p, and so we're still going to get a good approximation, right? The problem is that if our lower bound is loose, then this p over p prime factor is going to make us very small. It's going to make us very slow, right? So we want a lower bound in order to get a good approximation factor, but we don't want the lower bound to be too bad. So any thoughts on what might be a decent lower bound? Something that definitely is a lower bound, but is hopefully not too far from opt. Yes?
You can use a 2 approximation.
You can use a 2 approximation. How would I find the 2 approximation?
Maybe like run the algorithm with bigger value.
Yes, I could definitely start by running the algorithm with a large value of epsilon, and in practice that might be a good idea. But even if I'm running the algorithm with a large value of epsilon, it still depends on a value for p, on knowing a value for p. Right, so I need some kind of lower bound that I can pull out just by looking at the problem. Right, so if you had to really quickly come up with a decent solution to the knapsack problem, what would be the first thing to do? Yes?
Maybe just like greedily choose the best price per size.
Well, so again, that's the right thought. And in fact, it's a little simpler than that, because if you look at the size of an item, either it fits in the knapsack or it doesn't, right? If you're only choosing one item, then all that matters is whether it fits in the knapsack. And if the item doesn't fit in the knapsack, then there's no point in considering it as part of the problem at all, right? So we can just assume that all of the items fit in the knapsack. Now, if all of the items fit in the knapsack, which one should you choose? If you're only picking one. Yeah?
The one that gives the most profit.
Exactly. So one obvious lower bound is the maximum profit of an item. Definitely lower bound, because you can always put that item into the knapsack. How bad of a lower bound is it? Yes?
It's at least p over n.
Right. This is at least opt divided by n, right? The best you could hope to achieve is that every single item in the instance has the same profit, and you can fit all of them. So the most you can achieve is n times pi, right? Or sorry, I'm using p now. P is less than or equal to n times the max of the pi's. And so this lower bound is accurate to within a factor of 1 over n. And so now we can go back here, right, and look at this runtime and say, well, p prime is at least p over n. And so when we plug that in to our dynamic programming table, the width is n over epsilon times p over p prime, which is at most n squared over epsilon. Okay? And the nice thing about this is that we know this width without having to guess p, right? We don't need to have any knowledge of p in order to know how big to make the dynamic programming table. Okay? It did slow us down by a factor of n, though, compared to the algorithm that knows p. Yes?
Don't get a better rule now if we actually sort the items by this ratio and implement resolution?
There are many ways to get better lower bounds, yes. And so there's a greedy algorithm for knapsack, which, as you suggested, basically sorts the items by their profit density, right? The ratio of profit to size, and then includes items in decreasing order of profit density until the knapsack is full. And I don't recall what approximation value it achieves, but it is a certain constant, I think. Okay? I'm not sure it's a constant factor approximation, but I think that it might be. Okay? But we're here going for a fully polynomial. We're going for a fully polynomial approximation scheme, and that's better than you can achieve by that greedy algorithm. Okay? So here we have an epsilon approximation with an n squared over epsilon running time, but we can at least improve the running time, going back to the idea that was first proposed of binary search, right? So here we essentially started with something that is way off, and that made our algorithm a lot slower, right? But if we use binary search, we can improve on that runtime. Okay. And so what we're going to do is we're going to try to determine, for some guess, and we're going to ask, is that guess bigger than the optimum, sorry, I'll continue using p, over 1 minus epsilon, or is it smaller than p? Okay. Are we way over or are we under? Okay. And if we can answer this question, right, there's a third possibility, which is that we're somewhere in the middle, but that means that we're really close to p, right? If we're really close to p in our guess, then our scaling algorithm will run nice and fast. So we just have to get close to p. We don't have to get p exactly right. Okay? And so if we are able to answer, if we're in one of these two situations, we'll be able to binary search for something close to p. Okay? So the question is, can we differentiate these two cases quickly? Okay. So if we are in a situation where our guess is bigger than, sorry, let me use opt here. And let's use p for our guess. So if our guess is bigger than opt over 1 minus epsilon, then the optimum value is scaled to n times 1 minus epsilon over epsilon p times opt, which is strictly less than n over epsilon minus n. Okay? If we have guessed too large a value, then the scaled optimum will get too small because we scale down by our guess. Okay? Which means that you won't find a solution of value at least n over epsilon minus n. And remember, in our dynamic program, that's what we looked for, right? We said that when we had p correct, there was always a solution of value n over epsilon minus n, and so we would find it by using the dynamic program. So this tells us that we've overestimated opt because we found a solution that was too big. Sorry, because we didn't find a solution that we expected to find. If, on the other hand, we guess a value of p that is less than the optimum, well, in that case, the opt will scale to something which is at least n over epsilon minus n, which means that we will find a solution of that value. Okay. Now, if we've dramatically underestimated, this solution that we found may be very far from optimal, right? If we've made a terrible underestimate, then the optimum might be something like n squared over, might be something like n over, might be significantly larger, right? But it's not going to, we can stop as soon as we find a solution of this value, okay? Notice here that the runtime that we get, I should have mentioned this, is n times this, right? It's n cubed over epsilon because we have n rows in the dynamic programming table, okay? But if we're underestimating, we will find a solution of width n over epsilon, and we will find it in the original algorithm's n squared over epsilon time. Because we can stop as soon as we find a solution of that value, even if there is a much bigger solution. Okay? So basically, when we make our guess, we only need to explore the table out to size n over epsilon, which means that the runtime of the dynamic program to decide which case we're in is only n squared over epsilon. Okay? So each guess costs only order n squared over epsilon time, which is the same as we had when we knew p. The remaining question is, how many guesses do we need? So when you're doing a binary search problem, what determines the number of the guesses that you make? Besides the guessing procedure, what do I need in order to start my binary search? Yeah?
A range.
A range, right? And what about that range determines the time that it takes for me to do the binary search? Well, how big it is, right? If I'm cutting the range in half each time, then the size of that range determines my time, right? So here we need an upper bound and a lower bound, right? So we need starting upper and lower bounds. And we can stop when the bounds that we have are within 1 plus or minus epsilon of each other. Right? Because if we've got the bounds to within 1 plus or minus epsilon of each other, actually we can stop when they're yeah, let's keep it at this to keep it simple. Right? So how many, so what upper and lower bounds should we start with? Right? How can we, what's a good lower bound and what's a good upper bound that will let us stop with a small number of iterations? Well, we already came up with a decent lower bound, right? max pi, right? And the upper bound, what's our upper bound? Well, we also have an upper bound, right? Which is n times, or which is the sum of the pi's, which is at most n times the maximum of the pi's. Right? So initially, the ratio between the upper and lower bound is n. We want the ratio between the upper and lower bound to be small, so we're going to work in terms of ratios, right? I'm going to look at the geometric ratio between these two quantities, right? And I'm going to keep on cutting that geometric ratio. I'm going to look at the geometric mean between those two quantities, right? I'm going to try the square root of the upper bound times the lower bound as my initial guess, right? And each time I do this, I'm going to shrink the, I'm going to square root the ratio of the two bounds. Yes? By a square root. The initial ratio that we have is n. The target ratio between the lower bounds is 1 plus epsilon. So the question is, how many square roots do you need in order to go from n down to 1 plus epsilon, right? Or to put it another way, how many times do you have to square 1 plus epsilon in order to reach n, right? So the number of iterations I is such that 1 plus epsilon to the 2 to the I power should be equal to n. And sorry, I'm just looking at the time. You can solve this and find that the number of iterations is logarithmic in n and 1 over epsilon, right? So it's small. So we only have to do a few iterations, and each iteration has this n squared over epsilon running time. So basically, we can now do an approximation algorithm with a running time of n squared over epsilon times some log factors. Yes?
We 1 over epsilon?
Oh, thank you. Okay, so what we've done here is we started by developing a pseudo-polynomial algorithm, and then we showed how to scale it in order to get an algorithm, to get a fully polynomial approximation scheme. And you can basically always do this, okay? If you have a pseudo-polynomial algorithm, you can use our scaling and round down technique in order to give yourself a fully polynomial approximation scheme. Now, the reason that we were able to do this was that we had this pseudo-polynomial algorithm. And turning back to complexity theory for a second, the fact that there is a pseudo-polynomial algorithm means that the knapsack problem is what's known as weakly NP-hard. Okay. A weakly NP-hard problem is one where, in order to make it really hard, you have to use really big numbers. Okay? There are other problems which are NP-hard even if the numbers in them are small. And this includes all of the problems that don't have any numbers in them. So, for example, the Hamiltonian path problem is a problem about finding a path in a graph, and there are no numbers associated with the problem. So you're not going to have a pseudo-polynomial algorithm for that because there's nothing to be pseudo-polynomial in, and you can't solve it exactly because it's NP-hard. Okay? But knapsack is a weaker kind of NP-hard problem where it becomes polynomial time solvable if the numbers are small. Okay, so there's this tight relationship between pseudo-polynomial algorithms and weakly polynomial weekly NP-hard problems. Okay? Okay, that ran a lot slower than I liked. Let's take our 2-minute break, even though we're close to the end of class, and then I'll say a little bit more about this fully polynomial approximation scheme. Yes.
Can't we get rid of binary search to some reason that we initially approximated interrupt the certain constant?
Except that in order to approximate to within a certain constant, you're essentially going to need to do a binary search. That is not going, the runtime for that binary search is not going to depend on epsilon anymore, but it is still going to depend on n.
Is there not an easy algorithm which approximates up to constant factor of 2?
I have to go and look. I don't recall. Obviously the greedy algorithm has some factor of approximation, but it might not be constant. I need to go remember. It might be like logarithmic. I mean, there are many things that it could be besides a constant factor. Okay. Now again, whatever factor it achieves, you can then do a binary search whose runtime is the log of that factor. Right? Now actually, another thing that you can do, which I didn't mention, is you don't really need to binary search among all possible numbers, because really, you know that your solution is some power of 1 plus epsilon. You only need to look at powers of 1 plus epsilon between the lower bound and the upper bound. And so the number of those powers is only log n over epsilon. And you can now do binary search among those powers. So the number of queries you need is actually just log of log n over epsilon. So it's tiny. It's not worth trying to optimize further. Okay, let's resume. I showed you how to get from a pseudo-polynomial algorithm to a, sorry, I showed you, we saw how to get from a pseudo-polynomial algorithm, how to turn that into a fully polynomial approximation scheme. Now, interestingly enough, you can also turn any fully polynomial approximation scheme into a pseudo-polynomial algorithm. Okay. That is, if you have a fully polynomial approximation scheme for a problem, then that problem can be solved by a pseudo-polynomial algorithm. There's a polynomial time solution if the inputs are bounded by small integers. Right? And it's very easy to see that. Right? Suppose that the optimum is bounded by some integer t. And we have a fully polynomial approximation scheme that runs in time polynomial in n and 1 over epsilon. How can I get an exact algorithm Yes?
Use epsilon equals 1 over t.
Exactly. I'm going to set epsilon equal, I'm just going to be careful, 1 over 2t. Right? So now my fully polynomial approximation scheme runs in time polynomial in n and 1 over epsilon, which is polynomial in n and t. And it finds a solution of value at least t times 1 minus epsilon, which is t times 1 minus 1 over 2t, which is at least t minus a half, and therefore, if the solution is an integer whose value is at least t minus a half, then what is the value I have found?
T.
Well, it's t. Right? So if you're working with problems that have only integer solutions, a fully polynomial approximation scheme immediately gives you a pseudo-polynomial algorithm. Okay. So we've seen this one technique, and actually is a kind of a formal sense in which this is the only technique. Somebody wrote sort of a complexity theory paper that basically showed that any fully polynomial approximation scheme is basically doing scaling and rounding. It might be hiding, but it's essentially doing. And you can, I mean, one way to say that is that, well, okay, give me the pseudo polynomial, give me your fully polynomial approximation scheme. I use this transformation to turn it into a pseudo polynomial algorithm, right? So now I have a pseudo polynomial algorithm, and now I can take that pseudo polynomial algorithm and apply the scaling technique. So it is indeed true that any algorithm that can be approximated this way can be approximated by taking a pseudo polynomial algorithm and using scaling, because you can get the pseudo polynomial algorithm from the approximation scheme. Okay? All right, so that was the general technique for fully polynomial approximation schemes. It's used frequently. But sometimes there aren't fully polynomial approximation schemes. Sometimes you have strongly NP-hard problems. And that means there is no fully polynomial approximation scheme, right? Because if there were a fully polynomial approximation scheme, then there would be a pseudo-polynomial algorithm, and that would mean that the problem is not strongly NP-hard. Yes? I'm throwing a lot of definitions around, so if it doesn't make sense, you should ask. Okay? So what about these other problems? Well, so now we can go back to polynomial approximation schemes. Okay? We're going to sacrifice something in our runtime dependence on epsilon, but we're going to be able to solve or address a broader class of problems. And here, there's a very powerful technique known as enumeration. And I'll introduce it to you today, and we'll fill in the details on Friday. Okay. So we're going to go back to the load balancing problem. Actually, looking at the time, no, let me reorder this thing a little bit. So this load balancing problem is an instance of what's called scheduling theory. Which is this gigantic class of problems involving scheduling jobs on machines. Okay. It has developed into its own subfield of computer science and optimization, looking at all of the different flavors of scheduling problems. Okay. So there are, in fact, so many flavors of problems that they have developed a special notation for describing which problem it is that they're working on. Okay? So one thing that you can specify in scheduling theory is the machine or machines type that you're working with. You might be working with one machine. Okay? There are interesting questions you can ask about scheduling jobs on just one machine. I'll mention a couple of them in a minute. You can also specify that you are working with a whole bunch of identical machines. Okay? And if you have identical machines, this notion of PI, the runtime of a job, it's the same on every single machine. Okay? But you know, at a place like MIT, that's not true, because some of the machines were bought 5 years ago, and some of them are more recent. So there's this notion of what's called Q, related machines. sorry, so usually J is used to represent the jobs, so I'll say PJ. So when you have related machines, you say that machine I has a speed SI, and now the runtime of your job, if you run job J on machine I, the runtime is PJ over SI. Okay? But even that doesn't capture what can be going on modern computers, because some of your computers might have GPUs and just have completely different runtimes from the machines that don't have GPUs, not in a linear scaling fashion, but depending on what kind of job you're running. So these are called unrelated machines. And it's really not fair that they decided to use R for unrelated machines, but that's what they did. Okay? So you've got these different machine types. Now, the next thing that you can specify is a variety of objective functions. So, for example, you often start by talking about CJ, which is the completion time of job J. And what we were looking at was max CJ, right? The completion time of the last job in the schedule. Right? But you could instead talk about the sum of the CJs. Now, why would you be interested in the sum of the CJs? Well, if you throw in a 1 over n over here, then you're talking about the average completion time. Right? And this might be important if your jobs are people and you're trying to provide service to people, and what you care about is people's experience on average as opposed to the one outlier person who was unlucky. Right? Sorry, let me back up to my notes. You might also talk about having an indicator variable uj for saying, oh, sorry, you can refine this even further. You can talk about sum of wjcj, which is about weighted average completion time. If you care more about some jobs than others. Okay. Now you can also define a uj indicator variable, which is one, if the job finishes after its deadline, DJ. Okay, and then you can talk about the sum of the UJs, the number of late jobs, right? Or the sum of the WJ UJs. Okay. So there's this whole collection of objective functions. And if that's not enough, there's also all sorts of what are called side constraints, although that's a bit of a misnomer. It's just sort of variations on the scheduling problem. And these include things like jobs having release dates. RJ, tell you when the job arrives so that you can start doing it. You're not allowed to start a job before its release date. Okay. You might have the deadlines that I already mentioned in the late jobs description, right? You might have precedence constraints. Which is a relation saying that this job cannot be done until that job finishes. Okay, which makes a lot of sense in programming, right? If you need the output from one job in order to be able to start executing another job. You might also have preemption. Where you can stop a job in the middle and restart it on a different machine. Okay? So this is like being able to solve the job in fractions. Okay? Yeah, it gets even more esoteric. They have something called flow shop, where a job has to be run on several different machines in order. Okay? And open shop, where it has to be run on several different machines, but not but in any old order. So this shows up more in manufacturing, where you're manufacturing physical objects, and like first you have to attach the soles, and then you have to put in the uppers, and then you have to add the laces, and all different machines do all of these things. Okay? So they take all of these things and use them to summarize the problem they're working on. So we were working on at what's called P C max. And so this is how you do the notation, right? You give the machine type, then you give the constraints, of which we didn't have any, and then you give the objective function. Okay? And if you think about it, given the number of job types, number of machine types, and the number of objective functions, and this is just scraping the surface, and the number of constraints, you basically have a combinatorial explosion in the number of possible scheduling problems that you can work on. Right? And so actually, some of them have never been worked on, right? Which is great. Right? I was at a conference around 2000 something, and I saw one of my friends there, and I said, let's solve a scheduling problem. And so we took a walk, we picked a problem out of the hat, and we solved it, and then we wrote a paper about it. Right? So it's like this almost unlimited supply of research problems. Right, to just find another scheduling problem. And somebody actually wrote years ago a scheduling problem classifier that sort of takes all the scheduling problems and uses a large database to tell you for each scheduling problem what is its status. Like, has it been shown to be polynomial time solvable? Has it been shown to be NP hard? Right? And it does weird things like show you the hardest problem that is not known to be NP hard, and the easiest problem that is not, because there are reductions between these problems, right? If you add constraints, it usually makes the problem harder. So you might want to work on the problem without constraints before you work on the problem with constraints, and so forth. Okay? And so there are techniques that are applied quite broadly in this area, and whole books about scheduling theory, and basically it is a career you can enter if you want a particular subfield of optimization. And of course, it has tremendous applications in practice, right? The airlines care about scheduling, the delivery companies care about scheduling, anybody with a computer cares about scheduling, right? It's all over the place. But you can also just see it as one specific branch of algorithms. And so we will be looking at some more scheduling problems as wonderful driving examples for the approximation techniques that we'll be seeing, that we'll be looking at in the class. So that's it. I'll see you on Friday.